Assalamualaikum and hello everyone. We are gathered once again for the fourth lecture of physical geology, which is the introductions to structured geology topic. This topic will address two main course learning outcomes, which are number one, describe the main type of rocks, minerals, and fossils and how they are formed. Number two, explain the basic concept involved in formations of geological materials. By the end of this lecture, students should be able to number one, define the concept of deformation which lead to the formations of various structures. Number two, explain the stress-strain relationship with emphasis on brittle and ductile deformations. Number three, describe megastructure such as faults and fault. Lastly, to evaluate the significance of structured geology in the petroleum system. The fundamental question regarding this subject is what exactly is structured geology? Structured geology is the study of the architecture and geometry of the Earth's crust and the processes which shape it, and it also can be defined as a branch of geology that analyzes the change in shape of rocks bodies, which is strain produced by tectonic forces, which is stress. The importance of structured geologies include natural hazard study. Structured geology study the Earth's crust deformations and fault system, which is essential for understanding earthquake and volcano hazard. By analyzing geological structure, they can assess the likelihood and the impact of natural disaster, helping to save life and protect properties. Number two, understanding geological formation. Structured geology helps us unravel the Earth's history and how geological features were formed. It provides insight into the processes that shape landscapes, including mountain building events and the formations of mineral deposits, aiding our understandings of the Earth's past and its ongoing changes. Number three, constructions and geoengineering. When constructing building, bridges, tunnel, or any infrastructure, it's crucial to consider the underlying geological structure. Structural geologists help assess the stability of the ground, potential risk from landslides or subsidence, and recommend engineering solutions to ensure the safety and durability of projects. Lastly, explorations of natural resources. Structured geology plays a key role in locating valuable natural resources like minerals, oil, and gas. By analyzing geological structure and their relationship to resource deposit, geologists can guide exploration effort, making resource extraction more efficient and sustainable. Before that, let's have some understandings on the stress and strain. Stress is the measure of force applied to a given area, expressed as force per unit area, which is commonly referred to as pressure. It can be quantified using various units such as pound per square inch (psi), bars, kilobars, megabars, or the international standard unit Pascal (PA), with larger value expressed in megapascal (MPa) or gigapascal (GPa). There are three types of forces: compressional stress, tensional stress, and shear stress. Compressional stress involves forces that push material together leading to compressions or shortening. It occurs when opposing forces act with each other attempting to reduce the material length. Tensional stress is the force that pulls material apart, causing them to elongate or stretch. It occurs when two forces act in opposite directions along a material attempting to increase its length. Shear stress occurs when forces act parallel to each other but in opposite directions, causing this material to slide or deform sideways. It induces a change in the shape or orientations of the materials without altering its volume. Strain is a measure of deformation in materials and describes how they change in dimension, including length, angle, and volume when subjected to external forces. It quantifies the extent to which material shape or size has altered under stress. Strain is typically expressed in dimensionless unit, indicating the ratio of the change in dimensions to original dimension, helping engineers and scientists understand how material responds to the applied forces and stresses. There are three types of strains that associate with type of stress: longitudinal strains, volumetric strains, and shearing strain. Longitudinal strain is a type of deformations that associate the change in length after material has been introduced either to compressional stress or extensional stress. The calculation involved the ratio between the final length and the original length. Volumetric strain is a type of deformation that associates the change in volume after materials has been introduced to compressional stress. The calculation involved the ratio between the final volume and the original volume. Shearing strain or rigidity strain is a type of deformations that associate the change in shape after material has been introduced to shear stress. The calculation involved the ratio between displacement of the surface under tangential force and the original positions of the displaced surface. The stress-strain curve shows the relationship between stress and strain, which is a measure of how much a material deforms under load. In general, the stress is directly proportional to the strain, meaning that as the applied stress increases, so does the strain. The relationship between stress and strain on how material responds to stress is represented by a value called Young modulus. However, this kind of graph only happens in elastic regions, where the material will return to its original positions after stress is applied. Young modulus depends on materials' physical properties and is determined through laboratory analysis involving various pressure and strain measurement. This resulting data is used to create a stress-strain relationship graph, and the slope of the best fitting line represents the material's Young modulus. Since mineral constitutes rocks building blocks and each mineral has a specific Young modulus value, the mineralogy of rocks greatly influences its deformations behavior. Once the material reaches its individual yield stress or yield point in this region, it progresses into the subsequent stage known as the plastic region. In these plastic regions, the material undergoes irreversible deformations and no longer returns to its original shape or positions. Continued application of stress on the material will eventually lead to the attainment of ultimate stress. At this point, an ultimate strain occurs, marking the material's failure point. It is in this phase that the materials begin to fracture or become brittle. With the understanding of stress and strain, we can also understand on how the Earth's crust is deformed. The origin of the stress affecting the Earth's crust thus deform the rock is known to be from these three sources, which are plate tectonics, igneous intrusions, and isostatic adjustment rebound. Since we already covered plate tectonics in the previous class, let's focus on igneous intrusions. When molten rock, referred to as magma, infiltrates the Earth's crust, it can trigger stress and deformations. As magma ascends from the mantle and infiltrates the overlying rocks, it can induce deformations in the surrounding geological formations. In this initial stage, as magma ascends, it exerts a tensional stress leading to uplift. During this phase, the rock exhibits elastic deformations behavior, meaning it can return to its original positions once the stress is relieved. However, as the magma intrusion progresses, the stress intensifies. With increased shear stress, the rocks undergoes plastic deformation, which involve permanent deformations without returning to its initial state. Eventually, in the second stage, the shear stress surpasses the rock's shear strength, leading to rock's failure. This failure indicates by the initiations of fracture or faults. In this third stage, stress continues to be applied above the points of failure, resulting in the further shear failure and the opening of tensile fractures. Next will be the adjustments or rebound. Isostatic adjustment or rebound occur in response to change in distributions of weight on the Earth's crust. For example, during glaciation, the weight of ice sheet decreases the crust beneath them. When this ice sheet melt or recede, the crust slowly rebound or readjust to its previous positions. This process can lead to vertical crustal deformations, causing the lands to rise or sink over geological timescale. In another scenario involving mountain, the top image illustrates the mountain initial position when its roots extending into the mantle. When erosions and weathering take place on the mountain, it results in a reductions in its mass and density on top. So these alterations has an impact on the state of isostatic equilibrium. The counter-react that loss of mass due to erosions and uplifting event occurs. This uplift is a mechanism that aims to restore the isostatic equilibrium that has been disrupted by the erosions-induced mass reductions that been happen on the top of the mountain. However, this process of uplift also gives rise to stress and deformations within the geological structure. To understand the isostatic adjustment better, let's take this analogy. It's like walking off the boat when your wake is removed. The boat bobs upward and rises in the water. Get back in, and the boat bobs down in response to your wake. Back to the geological case, the crust is analogous to the boat and the mantle is the water, with the crust bobbing up and down in response to the thickening and thinning of the crust. Let's proceed with how the Earth's or rock's layers behave under different regions. Under elastic and plastic regions, the rock's layers or crust will fold with different type of formations, while beyond the plastic regions, the rock's layer starts to break apart and produce fracture or joints or even displace, where we call it as fault. Compressional stress is frequently associated with formations of fold and faults due to its characteristic behavior. Tensional stress consistently leads to fracturing and faulting, primarily caused by its elongational motion. Shear stress, on the other hand, tends to induce bending and breakage in geological structure. Okay, now let's have a look on the first structural deformations known as folding. Fold in structural geology is a result from a plastic deformations of rocks, primarily due to compressions resulting from tectonic activities. This geological structure manifests as bend or curve in rock's layer. There are two general types of folds, namely seam-form and antiforms. Seam-form is a type of structural deformation where rock's layer form a concave shape resembling a trough, and antiforms where rock's layer exhibit a convex shape resembling an arc or crest. Anticline is a common term referring to antiforms, while syncline is a common term referring to seamform. These shapes were formed due to the compressional stress from different angles. The picture below shows an outcrop with structures of syncline and anticline. Anticline that is capped with an impermeable rock layer like shales make excellent trap for petroleum. Hydrocarbons are positively buoyant in the earth, causing them to rise upward through a rock's pore space until they are trapped by the impermeable shale layer. Once more, foldings occur when a rock is being compressed and the temperature and pressure are just high enough for plastic deformations to occur. This illustration shows the typical terminology used to describe the anatomy of the folds in geology. The hinge point, the hinge zone, or the hinge lines refers to geological term denoting the point of maximum curvature located between two limbs or flanks of a fold. The fold axis, on the other hand, is a line that connects all the hinge points and maintains a consistent orientation to define the overall shape of the fold. Finally, the axial plane is an imaginary surface that encompasses all the hinge lines and the fold axis. These three terms are commonly employed to characterize fold structure. It was noting that geological folds can be significantly varied in terms of their wavelengths, ranging from just millimeters to several kilometers, as well as their amplitude. There are plenty more types of folding based on its occurrence and stratigraphy. Asymmetrical folds refers to the fold with 90-degree vertical axial plane. Symmetrical folds are characterized by limbs that mirror each other in terms of dips and orientations. The axial plane, which divides the fold into two equal halves, runs vertically. However, most of the time, folds can be tilted over on their sides during deformations, becoming either plunging or inclined as shown in this picture. The tilted hinge is called plunging hinge. Next, we have asymmetrical fold. Asymmetrical folds are characterized by non-vertical axial plane, where the limbs of the fold dip at different angles on either sides of the axial surface. In these folds, one limb typically has a gentler slope, while the other limb has a steeper slope. This results in an uneven appearance, with one side of the fold being elongated compared to the others. Next, we have recumbent fold. Recumbent folds are a type of folds where the axial plane is nearly horizontal or horizontal. This fold can appear as if the rock layer have been laid almost flat. The limbs of the folds are parallel or nearly parallel to each other, creating a horizontal or nearly horizontal orientations. Next, we have overturned fold. Overturned folds are characterized by steeply dipping axial planes where the limbs of the fold dip in the same direction but at different dip angles. In this fold, the rock layer on both sides of the axial surface are tilted in the same directions, but one side is tilted more steeply than the other. This results in a tilted or inclined appearance. And then we have monocline faults. Monocline faults involve a single steeply dipping limbs while the other limbs remain nearly horizontal. They often develop in response to faulting. Next, we have dome fault. Dome faults are upward circular structure where the oldest rocks are in the center and progressively younger rocks surround them. This fault results from the upward movement of materials. Lastly, we have basin fault. Basin faults are the opposites of dome fault with a bowl-like shape. The youngest rocks are at the center, surrounding by progressively older rocks. They form due to the subsidence. Beyond the plastic regions in brittle deformation, rocks undergo stress that surpass their inherent strength, leading to the creation of fracture or cracks and joints. Fractures indicates the actual breaking of rocks, while the term joint in geology describes open fracture where rock blocks remain relatively stationary along the fracture plane. When there is a movement and displacement of rock blocks, we classify it as fault. There are three common types of fault known as normal fault or gravity fault, reverse fault or thrust fault, and strike-slip fault or transform fault. A normal fault is a type of fault where the hanging wall, which is the rock layer above the fault, moves downward relatively to the footwall, which is the rock layer below the fault. This fault is typically associated with the extensional tectonic forces, such as divergent plate boundaries, where the Earth's crust is being pulled apart. Normal faults create a space between rock layers, forming fault blocks, and are characterized by steeply inclined fault planes. Next, we have reverse fault. In reverse fault, the hanging wall moves upward relative to the footwall. This fault occurs due to compressional tectonic forces common at convergent plane boundaries where plates collide. Reverse fault result in the shortening and thickening of rock layer. They often have steep fault planes and are associated with the formations of mountain ranges. Lastly, we have strike-slip fault. Strike-slip faults involve horizontal movement along the fault plane with little vertical displacement. This type of faults occurs at transform plate boundaries where two plates slide past each other horizontally. Strike-slip fault can be either right lateral, where the opposite sides appear to move to the right, or left lateral, where it appears to move to the left. The San Andreas Fault in California is a famous example of a strike-slip fault. In the oil and gas industry, faults are a significant contributor and one of the primary mechanisms for trapping hydrocarbon. This occurs when impermeable shale layer act as a barrier, preventing the upward migrations of hydrocarbon along the fault line. This concludes the introductions to structural geology, and you will delve into more detailed aspects of this subject in the structural geology course in the next semester. Our next topic will be the geological timescale. Thank you, and I wish you a wonderful day ahead.